Flight fuel planning and calculation is a critical process in aviation that ensures an aircraft has sufficient fuel for a flight while considering safety, efficiency, and regulatory requirements. Here's a breakdown of how it's typically done. Types of fuel considerations. Fuel planning involves calculating various fuel components to account for different flight phases and contingencies. 1. Taxi fuel. Fuel required for taxiing from the parking gate to the runway. Includes fuel consumed during ground operations, such as engine start and delays on the ground. 2. Trip fuel. Fuel needed for the aircraft to travel from departure to destination, including climb, cruise, and descent. Calculated based on distance, expected winds, temperature, altitude, and aircraft performance. 3. Contingency fuel. Extra fuel added to account for unexpected deviations such as weather, air traffic delays, or route changes. Typically a percentage of trip fuel, e.g. 5%, or a specific fixed value per regulations. 4. Alternate fuel. Fuel required to divert to an alternate airport if landing at the primary destination is not possible. Includes fuel for climb, cruise, descent, and landing at the alternate airport. 5. Final reserve fuel. Minimum required fuel to ensure the aircraft can remain airborne for a set duration, e.g. 30 minutes of holding at 1,500 feet above the alternate airport. This is a mandatory safety reserve. Extra fuel, discretionary. Additional fuel decided by the captain or operator based on anticipated conditions such as poor weather, expected holding patterns, or operational needs. Fuel planning takes into account a variety of variables. 1. Aircraft performance, fuel burn rates, maximum takeoff weight, MTW, and operational limits. 2. Flight plan routing, distance, waypoints, airways, and flight level. Direct routings may reduce fuel consumption. 3. Weather conditions, winds aloft, temperature, turbulence, and icing conditions. Favorable tailwinds can reduce fuel needs, while headwinds increase consumption. 4. Payload, weight of passengers, cargo, and baggage. Heavier loads increase fuel consumption. 5. Airport conditions, runway length, elevation, and expected delays, e.g. busy airspace. 6. Regulations. National and international aviation authorities, e.g. FAA, define minimum fuel requirements. Tools and systems for fuel calculation. Modern flight planning tools and systems streamline the process. 1. Flight Management System, FMS. Onboard computers calculate fuel requirements dynamically based on route and current conditions. 2. Dispatch software. Ground-based systems generate flight plans with fuel calculations using real-time weather data and route optimization. 3. Manual calculations. Pilots or dispatchers can use manual methods for backup, relying on tables, charts, or formulas. Example calculation. For a flight with the following parameters: distance 1,000 nautical miles, average fuel burn 5,000 pounds per hour, cruise speed 500 knots. Fuel calculation. Taxi fuel 500 pounds. Trip fuel 1,500 knots times 5,000 pounds per hour equals 10,000. Contingency fuel. 5% of trip fuel equals 500 pounds. Alternate fuel, 2,000 pounds assumed. Final reserve fuel, 3,000 pounds, e.g. 30 minutes of holding. Extra fuel, 1,000 pounds, discretionary. Total fuel required, 500 plus 10,000 plus 500 plus 2,000 plus 1,000 equals 17,000. Safety margins and monitoring. Fuel checks during flight. Pilots monitor fuel usage at regular intervals to ensure sufficient reserves. Unplanned deviations, e.g. headwinds or rerouting, may require adjustments. If the calculated fuel falls below safety thresholds, the pilot may reduce speed or altitude to improve fuel efficiency, divert to an alternate airport earlier than planned. Aviation authorities like the FAA, Federal Aviation Administration, or EASA, European Union Aviation Safety Agency, define strict fuel planning requirements to ensure safety. Airlines must comply with these standards to avoid penalties and maintain operational safety. This process ensures that the aircraft has enough fuel for all scenarios, maintaining a balance between operational efficiency and safety.